Great, thank you so much. Thanks a lot for the introduction, and also thank you for having me today. Okay, so today actually I'm giving a talk that I've never given before, so do bear with me. But this is a project that we started about 1 year ago, where two of my PhD students, Georgios Batzolis and Jan Stanzcuk, found this paper by Song et al. About score-based diffusion models for image generation, and got really fascinated by this. And this fascination was definitely infectious. And since then, we have been investigating these score-based diffusion models I'm going to tell you about in this presentation. And this is also joint work with Christian Etmann, who has been a postdoc in my group and is now working for an image compression company in London. So, right. Yeah, and maybe I should say, this is really, what I'm going to present to you is really the work of Georgios and Jan. They have really been working nonstop on these models and thinking about these models for the last year. And yeah, and I'm just going to report some of the things that we found. Okay, so first of all, the motivation for us was, as the title says, conditional generation, and in particular conditional image generation, where here are some examples of where this could be useful for. So you might want, in the context of image inpainting, for instance, you want to generate an image that is conditional on the image with the inpainting mask. So you want to do, use image generation as a way to do inpainting. So where inpainting is a task where you want to restore an image in a domain where it's damaged, or where you have some occlusions, for instance, like in this case. Or for super resolution, where you have a low resolution image and you want to generate a high resolution image. Again, the generation here is conditional on you knowing what the low resolution image looks like. Or this is actually the example that Georgios started off with. So this shoes data set, this followed us for quite some time, is this the idea that you have a sketch of a shoe or anything, right? But that was the data set. You have a sketch of something and you want to colorize it. And again, you can think of this as a conditional generation task. Yeah, and so please also interrupt me anytime if you have a question. Okay, so what is the aim here? So we are looking at generative models, and the aim of generative models is that we want to learn, well, we either want to learn a probability distribution, or we want to learn how to sample from a probability distribution given a finite number of samples, which will be our training set, right? And so there are various generative models that have been discussed in the machine learning literature in the past. So just a few words about them, categorized into likelihood-based models and implicit models. So likelihood-based models are trying to learn an approximation to the probability distribution directly. And examples of this are, for instance, variational autoencoders, normalizing flows, autoregressive models. And then another example or another type of generative models are implicit models, which are not trying to approximate the probability density directly, but trying to sample from this density without knowing it explicitly. Okay, And an example of that are GANs that I'm sure many of you have seen. Huh? And so another category, which is in a way also the foundation for these score-based diffusion models, are score-based models, where the idea is that you estimate the gradient of the probability density instead of the probability density itself. And these were the earlier models. You could use something like Langevin or something like this to sample. Okay, so this was kind of the idea. Now, why, could these score-based, in particular score-based diffusion modeling, by the way, do you see my pointer? This is important. Do you see this little hand if it goes over the slide? Okay, great, thank you. So why, thinking about all these different types of generative models, why could, in this context, the score-based models be interesting? Well, if these likelihood-based models and the implicit models, they have certain disadvantages when you look at the methodologies that currently exist. So likelihood-based models, for instance, since you want to learn a probability density directly, you can imagine that this is computationally quite complex, since if the kind of state of the art now is that you approximate this probability density by a neural network, which means that you need to have restrictions on the architecture that then guarantee that you get a probability density function. So you need to do normalization. This is sometimes also going hand in hand with imposing invertibility of layers of the neural network and so on and so forth. So this is usually quite computationally tough to actually realize. Implicit models, on the other hand, they are mainly based on adversarial training, which is, from a machine learning practical point of view, really unstable, and these models are usually very hard to train. Now, score-based models, and I haven't told you yet how they exactly work, but I'm going to in a moment, but score-based models, they have certain advantages. So since you're now not trying to approximate a probability density directly, you do not require this kind of normalization stuff that you require with this likelihood-based models. When you look at the performance of these score-based models, they are either on par or even surpassed generative models such as GANs. And in particular, and this is what we are also going to focus on in this conditional image generation context, they perform really well for solving inverse problems like we've seen, like inpainting or superresolution. Also, from a distributional point of view, you can actually, well, first of all, empirically, it seems that they have an improved distribution coverage, but also you have some theoretical guarantees, and I'm going to report some of them in this talk. Okay, so the whole idea behind score-based diffusion modeling really goes back to a result by Anderson from the 80s, which basically says the following. So you have a diffusion process, which is given here by this SDE, and under some assumptions on the coefficients F and G, and on the probability density function for at t equals 0, you can actually write down a reverse process for this diffusion process that is again a diffusion process, and that is given by this SDE over here, where in order to derive this reverse diffusion process, you need access to the gradient of the log density function. Okay. Right, and so now, so this is a result that is relatively old, but the the idea of why this could be interesting for image generation is, imagine you, so you have a data distribution, right, that you start out with, let's say a set of images, and then you send them through this forward diffusion process, and this forward diffusion process maps them to another distribution at time t equals capital T. That is your later we will call this your prior distribution, that you usually choose to be a very simple distribution, like a normal distribution. Okay. Now this result tells you that if you now do things the other way around, you start with a normal distribution and you have some way, okay, to access the gradient of the log density, then you can generate from noise samples, okay, from normally distributed samples, you can generate image samples from your distribution P0. Okay, and the whole thing about score-based models is how to approximate this. So this is where the name comes from, is also called the score, and how to plug this back in and then solve the reverse SDE, basically. So this is the whole idea. So again, here visualized. So you have your forward diffusion process that, let's say, maps you, for instance, to a normal distribution, and then you start with that. You solve your reverse SDE, and you go back to the data distribution. Okay, that is usually the complicated distribution that you want to sample from, like a distribution of images, of some kind of images. Okay. And this idea really goes back to this paper by Song from last year, where they combined this idea of score modeling with this result of Anderson. Okay, so just so how do you do this? So everything kind of depends that you can approximate this gradient of the log density, and so ideally, you would do something like this. So you approximate the gradient of the log density with a neural network. So this is the whole idea that we call S theta. And how do we train this network as theta? Ideally, we would optimize it with respect to this loss function here, where we are matching the score, the network as theta with the actual score, the gradient of the log density. Okay, and then we have some weighting here. So this is a kind of a weighted Fisher divergence that we would like to optimize. So now, sorry. So now the problem, of course, is that we don't have access to this, right? So we don't have access to the gradient of the log density, and so this is where things become now approximate. So instead of minimizing this in order to learn the S theta, what these score-based diffusion people are doing, or score-based modeling people actually in general are doing, is that they optimize this, where they replace the gradient of the log density by the gradient of the log of the transition densities. Okay, but a conditional densities, you start your forward diffusion at x0 and you end up at xt. Okay. Now this is not completely far-fetched, because is there a question?
One question, yeah.
Sorry for interrupting, but I was wondering what is the definition of PT again? Because say I start from some image data set that is this unknown density P. So does this come from already some kind of interpolation?
Yeah, that comes basically, so the PT is the probability density of xt it's the probability density of xt that is described by the trajectory of the diffusion process. Was this Sven, by the way?
Yes.
Yes. Okay. Okay.
Yeah, but can I ask as well, Rob here? So your flow, the forward flow is a flow from, or whatever we call it, diffusion, from your actual distribution to a reference distribution, like a Gaussian, let's say.
Yeah. Mm-hmm.
So the PT at the time t is something like an intermediate state in that flow from the actual distribution to the. Do I have to think of it as sort of, if I have an inpainting problem or a super resolution problem, I kind of am somewhere in between those two, and I try to use the information I've gained from learning this flow to flow back to the true distribution in some sense.
Yeah, exactly. Only, so the only thing is usually we don't really use PT directly in these score-based models, or actually the machine learning people do use it, but it's a little bit at the moment fishy because we don't. So what the machine learning people usually do is that they make this connection via Fokker-Planck with the ODE, but how it's trained, what I've just shown you, it's actually not clear whether it's fulfilled. So this, yeah. So, but this is there's lots of interesting things that one could do with this, which are not clear at the moment. But yeah, okay. Thank you. That's the idea, anyway. Okay, and so yeah, and so while this is now different to your original objective, it's actually when you write things down, you can see that this new objective is actually nothing else than the old one plus a constant that is independent of theta. So minimizing this is kind of equivalent to minimizing this. Okay. Now, very briefly, I don't know how many of you have heard about these score-based diffusion or score-based models in general. Yes?
Just in the previous slide. So why the second objective you can minimize it, you still don't have access to the expected the conditional log density, right?
So how do you do this? Right. Okay. So this is a good question. So you can do it in several ways. So if your let's go back here maybe. So if your F and G are simple enough, and usually, you know, F is chosen like an affine function, and G is usually chosen to be, you know, some kind of decreasing function in T or something, like some very simple function. Then this is actually, you can analytically compute this. You can analytically, because this is, so you can actually analytically compute this. Mm-hmm. If this is more complicated, you would need to solve the forward SDE several times.
Okay, thank you.
Yeah.
Can I enter the discussion here a little bit? Back to page 7.
Yeah.
So I've been following this work also. I find it very fascinating. And maybe I can add a little value here. So if you in particular, like Song Yong did, choose a Gaussian to be the reference distribution you want to get to, then you can, in fact, the distribution of PT of X given X0 will just be a Gaussian. Its score will just be linear.
Okay. Yeah.
So if I understand his philosophy correctly, the moment of approximation comes when we say we don't know the density Px0, but we have samples from it. We have our millions of images. So at that moment, this alternative criterion you replace by a sample average over your data set. And everything else is explicit. Now you're just fitting a score to a known thing, averaging over that data. Did I capture it right?
Yes, you did. So can I ask who you are?
I'm Andrew Barron.
Okay. Yes, great. Thank you. Nice to meet you. Yeah, super. Thanks a lot for the comment. Okay. So let me just go on. Let me just check the time because this is not so extremely important. I have till 11, right? I mean, I think I said what is more or less on this slide already. So score-based modeling has been around for a while, where people have tried to learn the score, but at fixed discrete, finite number of diffusion times, and then have not used the reverse SDE, but have used something like Langevin or Anil Langevin to sample with this learn score. But this idea of unifying this score matching and this diffusion models, so this kind of reverse SDE in continuous time, this goes back to this paper by Song. Okay, so right, I think again I said all of this already, but just so also Rob, you can have another idea of how this in between XTs look like. So the idea is that once you have trained the score, you sample from your normal distribution, which is here. This is just white noise basically in every pixel normally distributed noise, and then you integrate the reverse SDE, okay, with a method of your choice, and you get a sample of something that is close to the actual image distribution, okay? And I'll make this more precise in a moment. Okay, actually I make it precise now. So what Song actually proved is that if you choose this lambda t, so lambda t, if you remember, was the weighting. Sorry, and actually this is what we minimize, right? Was the weighting in my objective, right? In the score matching objective. And so what they proved is that if you choose lambda equal to the diffusion coefficient, G of t, then you can bound the KL divergence between the actual data distribution, okay, so the distribution of images, the true distribution of images, and the distribution that you get when you sample with this reverse SDE. And you can bound that by the weighted Fisher divergence plus the Kullback-Leibler between your normal distribution and the distribution at timed capital T, okay? And so in a way, although one nice thing about this is, since you are minimizing the DSM objective, so the one with the conditional with the transition densities, and hence you're also minimizing this objective, it means that you are also minimizing a kind of an upper bound on this KL divergence. This is not ideal in a way. Yeah.
I thought that the Fisher divergence arises as a derivative of the relative entropy along the path, so that wouldn't you need an integral version of the Fisher divergence here? You'd integrate it for t between 0 and 1. So when you defined your Fisher divergence, it had a t in it, little t, and we don't have any little t's otherwise. So I think you might need, clarify for me, but I think you might need that to be an integrated Fisher divergence.
Yeah, that's true. That's true. That's why, yes, thank you. That's true. Yeah, that's true. But the main problem with this is, so while this is nice to have, the main problem here is that you actually can't, this is not a quantitative bound in a way, because you can't really explicitly compute this, right? If you could, you wouldn't need to, you wouldn't need to do this, go to this DSM objective. So this is one disadvantage of this. Okay, so now this is a little bit of the background, right? So this is what this score-based diffusion idea looks like. And so something that we actually that Song already did, I'll tell you how they did it in a moment, but something we were thinking of using this for is for conditional image generation, okay? And so now I tell you first how we thought of doing this, and then I'll also go back and tell you what a kind of a general, more an approach looks like that other people have done for this conditional image generation task. So what we thought is, so how do you do conditional image generation with this idea? And so how we set this up is with this idea of multi-speed diffusion. And so imagine the following, okay? Imagine that instead of, imagine that your random variable that you want to model over time it consists of 2 parts. So I've now recalled this Z, and that consists of 2 parts, X and Y. And I define 2 diffusion processes now for these random variables X and Y that might be different to each other by choosing different coefficients here for the drift and for the diffusion part. Okay, so now I want to use this for conditional generation, and the idea of how to use it for that is the following. So now let's see if I can get this right now. So okay, so you have given paired data X, Y, Y, I. So going back to this example, you have given paired data that is, the observation Y, that is your image that you want to inpaint, and you have the original image. Okay, so this is your training set. No? Or in the case of super resolution would be these 2. And then what you want to do is you want to use this score-based diffusion to generate samples now from the conditional probability density of X given Y. Okay, so with what we have done before, what we know kind of how to do is the following. We diffuse both X and Y, right? Like with these 2 diffusion processes. And then we approximate the gradient of the log density, where this is now the density of ZT, right? So of XT and YT with the score. We could just do this in the same way as we did before. So how can we use this for conditional image generation? Now, the idea is the following. So if you are looking at the gradient of the log density, but now of the conditional density of xt given yt hat, where yt hat, okay, sorry, this is a little bit messed up here. Yt hat is now a sample that you take from, is basically y diffused up to t if you start with y, okay? So if you access the trajectory of your diffusion process at time t, and you sample from it, we call this yt hat, okay? And so what you can show, and this is a really simple computation, is that the gradient of the log density of this conditional density is the same as the gradient of log of the density of xt and yt hat. Now this, if you have trained it like this, right, is approximated with the first, I called this nx component of the learned score, right? Because you learned the score for both xt and yt. And so just think of them as concatenated vectors. Okay, so the first nx component are the ones for the reverse diffusion for xt. And so this is what we did, right? This is what we have done with this. Now, there is another step, right? Because what we actually want, if we do conditional image generation, we want to create x conditioned on y, right? Not on yt hat. But there is another thing that you can convince yourself of, is that if you choose the diffusion speed of yt hat, the diffusion speed of the diffusion process for y, if you choose this slow enough, if you choose it small enough, then the conditional log density you're actually interested in is approximately the same as the gradient of the conditional log density that you can compute, that you can approximately compute. Okay, and this is just here, just written down again more precisely. So you can, if you choose your diffusion speed, if you choose that if you choose that small enough, then then these two quantities are close to each other, right? Because you can bound them by 1 over the diffusion speed. So this is the idea. So is there a question maybe? Because this, I don't want to lose. Yes.
I do have a question. So, I mean, there must be a trade-off. Like if you, I mean, obviously if you let the diffusion speed go to 0, then nothing's happening on the second diffusion. So I guess you need a sweet spot somewhere, no?
Yes, and that is kind of that sweet spot.
I guess it's already there because it's expected, it's E of 1 over gy. If you set gy to 0, you have no bound.
No, exactly. Yeah, yeah. Mm-hmm. Yeah, that's a good comment. Are there more questions? Okay, so then, okay, so then it means if you've trained S theta with, in the same way as we did before, right? You can plug the first nx component of it back into the reverse diffusion process, thinking of it as something that approximately approximates the conditional reverse SDE with the conditional log density that you're interested in. Okay, so this is the idea. Now, well, yeah. So similar as we had for the plain vanilla score-based diffusion models, also for this multi-speed diffusion, you can prove the same thing about, or a similar thing about the approximation, or that of how well you actually approximate the true probability density of x and y. Okay, so this is just a generalization of the bound that we have seen before for the plain vanilla score-based diffusion models, where now the diffusion, this weighting is a matrix, because you are depending on you are potentially can change all the weighting now, not just for all times, but also for the different components that you have in xt and yt. Okay, so these are the diffusion coefficients. This is basically what this theorem says. If you choose lambda such that this is just a diagonal matrix with the diffusion coefficients of x and y in the diagonal, then you can get a similar bound as before. Okay, so this is how we thought of approaching this. Let me briefly, because this is a method that I'm going to compare with in a moment, let me show you how other people in machine learning have thought of doing this conditional image generation based on the score-based diffusion models. And one kind of prototypical approach is this conditional denoising estimator, where again you can see that it has been used, in a similar for similar kind of problems like super resolution, where this is just a comparison with with different super resolution approaches, and this is this conditional denoising estimator approach. Now, here the idea is, and you will see in a moment why I haven't started with this, but here the idea is that, again, you want to do conditional image generation by the conditional reverse SDE, okay? But they are learning the score in a slightly, well, actually quite different way that is not, I think, totally obvious why it works. Okay, so here again, so you want to solve the conditional reverse SDE and you want to replace this with a neural network. Okay, and now the neural network as theta is learned with this objective, where you are matching as theta, so your approximation to the score, with the gradient of the log of the conditional log density, but conditioned on x0. Where so which, well, so the only place where where basically the samples, or the distribution of the samples that you want to condition on comes in, is in how you sample for taking your expected value here. Okay, so in the objective itself, if you just if you don't look at this for a moment, the objective itself is not, it doesn't contain at all a condition on y. Where the condition on y comes in is on how you sample. And at least for us, this was initially quite puzzling. Why should anything like this, as theta that is trained like this, ever going to approximate what we are in this conditional score? So it wasn't at all obvious to us, and maybe this is because of the background, of the lack of background in SDEs and so on, but it wasn't obvious to us. But in fact, you can prove it. So this is the good thing. So you can actually prove that this objective that the CDE guys have been using, it actually makes sense, and that the minimizer of this is actually the same as a minimizer of the score matching objective that actually matches with the conditional score. Okay, so yeah, this is kind of nice. Okay, so what you see here is just, so then we ran some tests, or Georgios and Jan, they ran some tests for different examples of conditional generation, for different examples of conditional image generation, the ones that I've shown you before: image inpainting, super resolution, and this sketch to image. So the shoe goes to sketch of the shoe goes to the colored shoe. And what you see here is a comparison between okay, the CDE, which I've just shown you. So this is a kind of state-of-the-art conditional score-based diffusion approach, and this conditional multi-speed diffusion, denoising estimator that Georgios and Jan proposed. And these are just, what you see here is just so these are the first two are quality metrics for the reconstructed images, and this is what's it called again? well, so this is a quality measure for how well you are actually matching the distribution. So this is telling you how close your generated distribution is to the underlying distribution of images that makes up the whole of your data set. And then you have some more quality measures here for the distribution, which is this diversity, and also for individual samples. Okay, consistency, for instance, is in the super resolution case, you look at your super resolved image and then you downsample it again and you compare it with the low resolution image. Okay, things like that. And you see that there is no real winner here, right? So they are all kind of performing kind of equally well. I think the nice thing that we thought was just this conditional multi-speed idea was just that it seemed more natural somehow to do it like this, more canonical in a way. Yeah, so this was the idea. So here just a few examples, just so you see a few pictures. So this is for inpainting. This is the CDE result. This is the result with our multi-speed diffusion approach. Okay, so this we also have an Austrian example here. Quite fitting, I guess. And then you can also see how different, if you sample more often, of course, you get different realizations. Okay, so these are different reconstructions that you can get by solving the reverse SDE with the conditional multi-speed idea. So one last thing, or actually I should maybe stop. Yeah, why don't I skip this? Maybe just one thing. I mean, you can use this multi-speed diffusion idea also in other ways. And one way, for instance, is you could imagine that you transform your image into another domain, like the wavelet domain, for instance. And then you use different diffusion speeds for different scales in the for different parts in the wavelet coefficients. So you could diffuse for instance, the higher frequencies faster than the lower frequencies, and so on. And if you do this in a clever way, then you can actually save on sampling time. You can solve the reverse SDE quicker because you don't have to reverse diffuse everything for the same amount of time, but you can diffuse some bits faster, hence you're finished earlier. Okay, but let me just not talk about this and conclude. So I think score-based diffusion models are really interesting for generative modeling. And the reason why, which caught my interest initially, really was that, okay, there is machine learning definitely involved in learning the score, right? So you need to have a good way to learn the score. But once you have learned the score, everything is based on solving your reverse SDE. And if you have learned the score, still preserving certain properties, right? If you have, if you approximate the score well enough and things like this, you also get some guarantees for the reverse SDE. So this is somehow nice. I like this more than using a neural network directly to do generation or to solve a mathematical problem that you have. Well, multi-speed diffusion we have seen we can use for conditional generation. I've not really told you much about this multi-scale idea because I ran out of time, but that's another idea. This multi-speed diffusion for conditional generation really is kind of on par with the CDE estimator, but it comes with some maybe more natural motivation. And so some things I've mentioned at the beginning, I mean, there are lots of open questions still, and these are just a few of the things that we are looking at the moment. So one of the things that is missing in all of this is this connection to Fokker-Planck. Because we are only learning the score and not the probability density directly, right? So somehow this is something that is missing, and we're currently looking at whether we can rectify this in some way and put a Fokker-Planck constraint into the learning process. The other thing, I think there is a lot of nice numerical analysis that one could do for how to solve the reverse SDE more efficiently, because what Song et al. Did was basically just very standard approaches for the reverse SDE, just basically explicit time stepping. And similarly, if you would make the connection via Fokker-Planck, you could also focus on how to efficiently solve the reverse ODE instead. And so I think there is lots to do, because this is at the moment the bottleneck of these models, is that sampling takes more time than with other approaches. Okay, so thank you very much for your attention.